Somewhere beneath the surface of the Pacific, in water that should be cold enough to numb a human hand in minutes, something is wrong. The temperature gauges are climbing into territory scientists have never recorded. Not in a single summer, not in a single decade. In the entire span of modern instrumental history. And the strangest part is not that the ocean is warming. The strangest part is what that heat is now doing to the sky above it. For most of human civilization, we treated the ocean as a passive backdrop to the drama of the atmosphere. Storms were born in the air. Droughts were written in the clouds. The sea simply sat beneath it all, vast and silent, absorbing whatever the sky handed down. That assumption is now collapsing. Because the ocean has stopped being a bystander. It has become the author. Across the planet, buoys, satellites, and autonomous drifting robots are reporting sea surface temperatures that break record after record, not by fractions of a degree, but by margins that make climate scientists pause before publishing their own data. Heat that used to stay locked in the deep is surfacing. Heat that used to distribute evenly across seasons is now arriving in sudden, violent pulses. And every one of those pulses is rewriting the rules of the weather machine that keeps human civilization alive. This is the story of that machine breaking down, not in some distant, hypothetical future. Right now, in real time, measured by real instruments, confirmed by real institutions. This is the story of how the ocean absorbed more than 90% of the excess heat trapped by rising greenhouse gases quietly for decades without complaint. And how it may finally be releasing that heat back into the sky in ways nobody fully predicted. To understand what is happening, you first have to understand what the ocean actually is. Not a body of water, a battery, the largest heat storage system on Earth, holding more thermal energy in its uppermost 3 meters than the entire atmosphere stacked from sea, level to the edge of space. Water absorbs heat slowly, releases it slowly, and moves it around the planet on currents that can take centuries to complete a single loop. That slowness has always been humanity's silent protector. It smoothed out the shocks. It gave the atmosphere time to breathe. But a battery that has been charging for decades does not stay stable forever. Every joule of heat trapped by carbon dioxide and methane in the atmosphere has to go somewhere, and the vast majority of it has gone into the sea. Scientists have tracked this using deep ocean sensor networks, satellite altimetry that measures the tiny swelling of the sea surface as warmer water expands, and thousands of autonomous Argo floats that drift through the water column, diving and rising, recording temperature and salinity at every depth, then surfacing to beam their data to orbiting satellites. The picture these instruments paint is unambiguous. Ocean heat content has been rising for decades, and in the last few years, that rise has accelerated beyond what most climate models expected. Here is where the mystery deepens. A warmer ocean should not simply mean warmer swimming water. It means a fundamentally different relationship between sea and sky. Warm water evaporates faster, pumping enormous volumes of moisture into the atmosphere. That moisture becomes fuel, fuel for storms, fuel for rainfall events that dump in hours what used to fall in weeks, fuel for the kind of atmospheric rivers that can flood entire regions in a single pass. The ocean is no longer just warming the world, it is arming the sky. Consider what happened when marine heat waves began forming with increasing frequency in the North Pacific. These are not ordinary warm spells. A marine heat wave is a mass of unusually hot water that can persist for months, sometimes over a year, spanning an area larger than entire countries. The first major one to capture global scientific attention formed in the mid-2010s and was nicknamed simply the Blob. It devastated marine ecosystems, starved sea lion populations, triggered toxic algal blooms along the coast, and disrupted fishing industries that had operated on predictable patterns for generations. At the time, researchers treated it as an anomaly, a strange, singular event. It was not singular, it was a preview. In the years since, marine heat waves have become dramatically more frequent and more intense across ocean basins worldwide, from the Mediterranean to the Tasman Sea to the tropical Atlantic. Each one behaves like a regional furnace, radiating extra heat and moisture into the atmosphere directly above it, disturbing the pressure systems that steer weather patterns thousands of miles away. A patch of unusually warm water off the coast of one continent can shift the position of a jet stream that determines whether a distant nation experiences drought or flood. The ocean does not respect borders. Neither now does its heat. This is where the story turns from strange to genuinely alarming. The jet streams, those high-altitude rivers of fast-moving air that circle the planet and steer the parade of storms and high-pressure systems across the mid-latitudes, are driven by temperature contrast. Cold air near the poles, warm air near the equator, and the jet stream forms in the boundary between them, like a fence line drawn by physics. But the Arctic is warming several times faster than the global average, and the oceans beneath the ice are warming with it. As that temperature contrast weakens, the jet stream weakens too, and a weaker jet stream does something counterintuitive and dangerous. It begins to wobble. It develops deep loops and stalled waves that can lock weather patterns in Place E for days or weeks instead of the days that used to be typical. A heat wave that once would have moved through in 72 hours can now sit over a single region for 2, 3, 4 times as long, baking soil, draining reservoirs, and pushing infrastructure past its design limits. At the same time, the tropics are experiencing their own transformation. Sea surface temperatures in the regions where hurricanes and typhoons are born, the warm bathwater latitudes near the equator have been trending upward year after year. Tropical cyclones draw their power directly from the heat stored in the upper ocean. Warmer water means more energy available for a storm to convert into wind speed, and it also means storms can intensify faster than forecasters are used to predicting. In recent years, meteorologists have documented a sharp rise in the number of storms undergoing what is called rapid intensification, a jump in wind speed of 35 miles per hour or more within a 24-hour window. This is not a subtle shift in probability. It is a structural change in how these systems behave, driven directly by the extra fuel sitting in the water below them. Rapid intensification is not just a technical term. It is the difference between a coastal community having days to evacuate and having only hours. It is the difference between a storm making landfall as a moderate system and making landfall as a catastrophic one, with almost no additional warning. Emergency planners who once relied on forecast models built around historical storm behavior are now confronting systems that defy those models, because the ocean feeding them no longer resembles the ocean those models were built on. But heat is only half of the story. The other half is what warm water does to the water cycle itself. Warmer air holds more moisture, a relationship long understood in atmospheric physics. And for every additional degree of warming, the atmospheres substantially. When that moisture-laden air eventually releases its cargo, it does not fall gently. It falls in bursts. This is part of why regions across the globe have experienced a rise in extreme short-duration rainfall events, the kind that overwhelm drainage systems built for a climate that no longer exists. Cities engineered for the storms of the 20th century are now absorbing the storms of a warmer, wetter, more volatile ocean-driven atmosphere, and in many cases, they are losing. And yet, in a cruel twist of atmospheric physics, the same warming ocean that fuels catastrophic rainfall in one region can simultaneously starve another region of it entirely. As weather patterns stall under a weakened jet stream, some areas find themselves locked beneath persistent high-pressure domes, blocking storm systems for weeks, evaporating soil moisture, and deepening droughts that stress agriculture and water supplies. The paradox is real. A warmer, wetter ocean is producing both flood and drought, often in the same year, sometimes in the same country, driven by the identical underlying mechanism: more heat, more moisture, more instability, distributed unevenly across a planet whose atmospheric circulation is losing its old predictable rhythm. Scientists studying this shift are not working from speculation. They are working from an expanding web of observational evidence. Satellites operated by NASA and the European Space Agency track sea surface temperature anomalies in near real time. The Argo Float Network, an international collaboration involving dozens of countries, has placed thousands of robotic instruments throughout the world's oceans, each one diving to depths of roughly 2,000 meters and back on a repeating cycle, building a three-dimensional picture of ocean heat that simply did not exist a generation ago. The National Oceanic and Atmospheric Administration and international partner agencies maintain long-term ocean heat content records stretching back to the mid-20th century. And it is against that long baseline that today's anomalies stand out so starkly. What these records reveal is not a smooth, gradual warming curve. It is a curve punctuated by sudden jumps, plateaus, and then further jumps, patterns that researchers are still working to fully explain. Some of the acceleration appears tied to natural climate cycles like El Niño and La Niña, which shuffle heat between the ocean surface and the deep water in ways that can mask or amplify the underlying warming trend in any given year. But when scientists strip away those natural oscillations and look at the multi-decade trend beneath them, the signal that remains is unmistakably tied to the accumulation of greenhouse gases trapping additional energy in the Earth system, the overwhelming majority of which the ocean absorbs. There's another layer to this story, one that unfolds not at the surface, but in the slow, grinding machinery of deep ocean currents. The global network of currents that redistributes heat around the planet, sometimes called the ocean conveyor belt, depends on differences in temperature and salinity to drive its circulation. In the North Atlantic, warm surface water flows northward, cools, becomes denser, and sinks, pulling more warm water in behind it, a process that in turn helps regulate climate patterns across Europe and beyond. As polar ice melts and adds fresh water to that system, And as surface waters warm, some of the density contrasts that drive this circulation are weakening. Researchers using long-term measurement arrays across the Atlantic have documented signs of this slowdown, and while significant scientific debate continues over exactly how much it has weakened and how quickly it might change further, the possibility of a major disruption to this circulation system carries consequences serious enough that it remains one of the most closely monitored phenomena in modern oceanography. If that circulation were to slow dramatically, the effects would not be uniform or intuitive. Some models suggest parts of Europe could face sharply colder winters even as the planet as a whole continues warming. A scenario that sounds contradictory until you remember that regional climate is governed by the redistribution of heat, not simply its total quantity. A slower conveyor belt means less heat delivered to certain latitudes, even while more heat overall accumulates elsewhere. This is the uncomfortable nuance at the heart of ocean-driven climate change. Averages can rise while specific regions experience volatility, extremes, or even localized cooling, all stemming from the same root cause. Meanwhile, the consequences of ocean heat are not confined to the atmosphere above it. They are rewriting life within the water itself. Coral reefs, among the most temperature-sensitive ecosystems on the planet, have experienced repeated mass bleaching events, as marine heat waves push water temperatures beyond the threshold corals can tolerate. When water gets too warm, corals expel the symbiotic algae that give them color and much of their energy, turning stark white. And if the heat persists, the coral often dies. Major reef systems, including large sections of the Great Barrier Reef, have experienced back-to-back bleaching events in recent years with less recovery time between them than these ecosystems have ever had to endure. Coral reefs support an estimated quarter of all marine species at some point in their life cycle, despite covering a tiny fraction of the ocean floor. Their decline sends ripples through fisheries, coastlines, and food security for hundreds of millions of people who depend on healthy reef systems, directly or indirectly, for their livelihoods. Fish populations themselves are on the move, migrating toward the poles as they follow the cooler water their physiology requires, forcing fishing fleets to travel farther, disrupting international agreements built around the assumption that fish stocks stay roughly where they have always been. Entire regional economies built around specific species and specific waters are being forced to adapt in real time to a map that keeps redrawing itself. And there's a subtler, more unsettling piece of this story, one that connects the ocean directly back to the air we breathe. The ocean is not just a heat reservoir, it is the planet's largest carbon sink, absorbing roughly a quarter of the carbon dioxide humans emit each year. But warmer water holds less dissolved gas, a basic property of chemistry that applies to carbon dioxide just as it does to the fizz in a soda left out in the sun. As the ocean warms, its capacity to continue absorbing carbon dioxide efficiently may be gradually declining in certain regions, meaning more of our emissions could remain in the atmosphere rather than being buffered by the sea, potentially accelerating the very warming that is driving the ocean's transformation in the first place. Scientists are still working to quantify precisely how significant this feedback will become, and it remains an active area of research rather than a settled certainty. But the mechanism itself is grounded in well-established chemistry, and it represents exactly the kind of self-reinforcing loop that keeps climate scientists awake at night. It would be easy, faced with a story this vast, to feel that the picture is one of simple, linear doom. But the reality unfolding in ocean basins around the world is more intricate than that, filled with feedback loops that scientists are still mapping, thresholds that are not yet fully understood, and regional variations that defy easy summary. This is precisely why the ongoing effort to monitor the ocean, from satellites in orbit to robotic floats drifting silently through the abyss, matters so profoundly. Every data point collected today becomes part of the historical record, against which tomorrow's anomalies will be measured. Every improvement in forecasting models built from that data becomes a fee community facing a rapidly intensifying storm, a few more days of preparation for a region facing an emerging drought. There is also a quieter, more human dimension to this unfolding story, one easy to lose beneath the satellite imagery and the temperature graphs. Coastal communities that have fished the same waters for generations are watching those waters change in ways their grandparents never described. Farmers who once set their planting calendars by weather patterns as reliable as the tides are now facing seasons that no longer follow the old rules. Emergency responders are recalibrating their assumptions about how fast a storm can strengthen, how long a heat wave can linger, how quickly a flood can arrive. Across every one of these human stories runs the same invisible thread, tracing back to a body of water most people will never personally measure, but whose rising temperature is nonetheless rewriting the conditions of their daily lives. What makes this moment in the story so significant is not simply that the ocean is warming, it is that we are, for the first time in human history, watching it happen with enough scientific precision to understand the mechanism as it unfolds, rather than reconstructing it afterward from fragments of geological evidence. Ice cores and ocean sediment layers tell us that Earth's climate has shifted dramatically before, over spans of thousands of years, driven by changes in the planet's orbit or in volcanic activity. What is happening now is different, not just in cause, but in speed. The changes captured by today's instruments are unfolding on a timescale of decades, a blink of an eye by the standards of Earth's climate history, and humanity finds itself in the unprecedented position of watching its instruments record the story in real time. The scientific community's response has been to build an ever more sophisticated web of observation, prediction, and public communication. International panels synthesize thousands of research papers into assessments meant to give policymakers and the public an accurate picture of where the evidence points, complete with careful distinctions between what is firmly established, what is likely but still developing, and what remains genuinely uncertain. That distinction matters enormously here. It is firmly established that the ocean has absorbed the overwhelming majority of the extra heat trapped by rising greenhouse gases, and that ocean heat content has been rising for decades. It is well supported that marine heat waves have become more frequent and intense, and that warmer sea surface temperatures are associated with faster tropical cyclone intensification. It remains an active area of scientific investigation exactly how quickly systems like the North Atlantic circulation might change, and precisely how regional weather patterns will continue to shift as the ocean keeps absorbing heat in the years ahead. Locked in, and which parts are still being written, is not a weakness in the science. It is the science working exactly as it should, refusing to claim more certainty than the evidence supports, while still being clear about what the evidence does show. And what it shows, taken as a whole, is a planet whose engine room has shifted. For most of recorded history, humanity looked to the sky to understand the weather, clouds, wind, pressure systems, the visible drama playing out above our heads. But the deeper truth, the one only now becoming fully visible through decades of patient measurement, is that the real engine driving so much of what we experience as weather has been sitting beneath the waves the entire time, absorbing our excess heat in near silence, buffering us, far more than we understood, and now, increasingly, releasing that stored energy back into the atmosphere in the form of stronger storms, deeper droughts, and rainfall events unlike anything in the historical record. The ocean kept our secret for a long time. It absorbed the consequences of more than a century of industrial emissions without complaint, without visible protest, holding back a portion of the warming that would otherwise have already reshaped the surface world far more dramatically than it has. That silence made it easy to overlook. It made it easy to imagine that the atmosphere alone told the whole story of a changing climate, but the instruments floating through the deep, the satellites tracking the subtle swelling of the sea surface, the buoys recording marine heat waves as they form and spread, are telling us otherwise. The ocean was never a passive backdrop. It was always the hidden protagonist, absorbing the weight of a warming world, and now, for the first time in human history, we are watching in real time as that stored energy begins to rewrite the sky itself, one record-breaking measurement at a time, and the next chapter of that story is still being written right now in the water beneath our feet.